So, hello. Sorry to be in the situation we have right now, where I was very much looking forward to starting this course in person, but then tested positive for COVID a couple days ago, and as a result, unfortunately, need to start with remote teaching for hopefully only the first week of the course, but we'll have to see how things go. Um, Fortunately, yeah, my symptoms are fairly mild, but speaking does kind of test my voice a little bit. So apologies in advance for any coughing and things like that. I'll try to not do that too often, but it's a bit unpredictable. And thanks to Christoph for getting us all set up. I hope everyone can see my slides okay. And yeah, first off, I'd like to welcome you to the Geo-Python course for 2022. As I already alluded to a moment ago, very excited about returning to teaching in a classroom together, and hopefully that can continue as planned starting from next week. But the basic idea for what we're going to cover today in terms of the introduction for the course is just to give you first off a little overview of what the course is about, practical information, probably some things you already know, but the kind of details that you would need to get started in any course. And we'll talk a little bit about what a computer is and what computer programs are, because these sort of underpin the ideas of what is the whole focus of the course, and that is to learn how to program using the Python programming language. And notably, we're not assuming you have any programming experience before, so don't panic if this is sounding scary, because yeah, we're basically treating things in the course as if we're total beginners. Then we'll have a look at our course computing environment, we'll look at most of it. There's one problem at the moment with one of our cloud computing systems, so we'll probably have to talk about that in more detail next week. But at the very end of what we'll talk about today will be our Taste of Python lesson, where we will then be able to get a picture of what programming in Python looks like for the very first kind of first experience, I suppose. So that's where things are going. Maybe just to start with some brief introduction. So my name is Dave Whipp. I'm a professor at the Institute of Seismology, and I'm the person who's effectively going to be the main lecturer for the Geo-Python part of the course. I've been teaching Geo-Python since maybe 2015, when we first started a version of it, and it's sort of since evolved into what it is currently. And so I'm very happy to see you folks here interested in learning to program in Python, because this is one of the most fun courses for me as a teacher, and I very much enjoy it every year when this time of year comes around. Christoph, do you want to maybe introduce yourself briefly?
Yeah, maybe very briefly. My name is Chris. I'm a postdoctoral researcher at Dooley Toivanen's group, the Digital Geography Lab. So I work a lot with Python myself, and I'm going to be teaching kind of the second half of this course for the geographers and also geologists. No, it's not listed for geology, is it? I'm not sure. Which goes then kind of continuing from where we leave with this course, like where you know perfectly well how to program Python programs and dive a bit deeper into geography and GIS problems, which we also touch on this course there, so not saying that. And I'm very much looking forward to this other course, which is then in the second period, and I hope many of you join there too.
Yeah, thanks. And yeah, we do have two course assistants at the moment. Probably we will have a third, but I have not been able to pin anyone down to do that yet. But Mikko and Justus, do you want to at least say who's who and hello if you happen to be there?
Hello, I'm Justus. I'm a fifth-year geography student. I was a course assistant on this course last year. Here to help, so ask me not anything, but almost.
I am Mikko, fourth-year geography student. yeah, helping with the practical exercises. Looking forward to it.
Great. Okay, thanks. So that's a little bit of who we are. Some additional information maybe that's useful is our course web pages. So for period 1, we'll be using Geo-Python and the AutoGIS 1. These two courses are run simultaneously. And the web page is this geo-python.github.io. That is going to be the kind of main place where you find information about everything in the course. So all of the lessons will be there, recordings of the lectures and things like that will also be posted on that webpage, as well as links to all of the exercises. So that is the place to go for anything related to the course. And then in period 2, there's the AutoGIS webpage, which will be obviously more relevant for students who continue on to the second part of the course during period 2. So these are just here, obviously, to remind you. And I sent an email this morning. Some of you may have seen. I sent it quite late, I guess. But this Geo-Python page is also linked in that email so that you can find the course webpage. And we'll have a look at the course webpage in just a moment. Other practical things. So during the first period, we're going to be meeting on site. Ideally, all of us will be there. And this will be in the classroom that you're in right now in the Exactum, Wednesdays from 9:15 until about 12 o'clock noon. So those are the lessons where you can come and we'll basically kind of go through in a somewhat interactive way, learning to program during those lessons. In addition, we have some optional exercise sessions on Thursdays and Fridays where you can come and you can get some assistance from other students in the course and from the course assistants on how to complete the exercises. So we will have weekly exercises, and the Thursday and Friday sessions you can use to come and get some help for working on those exercises. It doesn't matter which one you go to. So even if you've registered for one, you can go to the other, and if you didn't register for either of them, you can go to either. If you want to go to both of them, you can. And if you don't want to go to any, that's also totally fine. These are optional sessions, but they are, from our experience, quite helpful for making sure you don't get totally stuck and frustrated, and you can keep progressing with things you're working on in the course. I think Christoph already said something about the AutoGIS course, so maybe there's not a need to really highlight too much here, other than the fact that this course does continue for the geography students in the second period with a different course code, so Geog 329-2, which is the Automating GIS Processes 2 course, or the second half of this one. First half is basically just Geo-Python, and that's where you'll kind of get into more applications of Python programming to GIS problems, and combined, this is then 10 credit points. So if you have any questions about that, I suppose you can ask myself or Christoph, but probably he's the expert on this one. Okay, so let's now maybe get a little bit of a sense of who you are. And to do that, I'm going to have to get out of the slides here for just a second. So there's this web page here, geopython.github.io/poll. And if you go to that page, you should see a question that is asking you which course you are enrolled in. And if someone's there in the classroom, maybe it's a good thing, like if there's a space on the chalkboard where you can write this web address, we might use it a couple different times, and it might be handy to have that written down somewhere on the chalkboard or something like that, so that people can refer to it. But this will take you to a page where you could basically just click a button and tell us which of the two courses you are enrolled in, or if you're not enrolled, you can also click the button to say, well, that you aren't enrolled. So take a minute and fill in your responses there, and then we'll continue in just a moment. Okay, so things seem to be sort of slowing down a little bit here in terms of the responses, but perhaps what you can already see is that we have a pretty even division between the students in the Geo-Python course, the geology course code. So Geoc 3030, and those in the Automating GIS 1 course, Geog 329-1. So pretty even split. I suppose that's not a big surprise. That's pretty often how it goes, although most years we do have a few more in automating GIS processes than Geo-Python. So maybe we have a bit of an anomalous year. We also have some students joining from Alto, so welcome to those students, and then maybe a few who are not yet enrolled in the course. And when we come to talking about some of the other course environment things, we're going to talk about the Slack system that we use for kind of chat-based communication. And in there, if you're having trouble with enrolling, there's a place where you can report enrollment issues that you're having. So hopefully I'll remember to come back to that. For those who are trying to get enrolled and having problems, we'll try to help you out. Okay. How about another question here? So let's do it like this. You should hopefully now see a different question about how much programming experience you have. So again, there's no shame in saying you've got none. Just feel free to be honest here. It's good that we get a sense of what the distribution looks like. So already I think you get a pretty good view of how things are kind of shaking out. That, it looks like the majority are people who have maybe a little bit of exposure to programming before, but haven't used it much, or it's been a while since they've done anything with it, and some who have a little bit more experience, and even a few who have kind of a fair amount, and of course some who are complete beginners. And so that's very typical of how things go in the course. We have a pretty good spread in terms of abilities, and we try to take advantage of that where we can by getting you paired up to work together, so that the students who are really without any experience at all are maybe working with someone who has a little bit more experience to help the two of you be able to learn from one another, because it's a quite useful learning experience even for a more advanced programmer to have to explain some of the concepts of coding to someone who's a complete new user. So that's what our sort of experience distribution looks like. For those who have some programming experience, we can move to another question now about which programming languages you've used before. But yeah, you can see, I mean, the majority here, again, not a surprise, Python and R are two of the most popular programming languages at the moment. And those are the two that seem to be most heavily used by you all. And let's ask maybe one more question here. And I got to hide the other question first. And that is, what are your expectations for the course? And so this, you can basically just type in something. It's kind of a free response type of question. And if I'm not mistaken, I think you can also vote if someone else submits a response you like. I think you can click to vote and support their suggestion. So please feel free to add your. We hope you pass the course too. So I think people are still maybe filling in some responses here. You can continue to do that while we just look these over briefly, but obviously you can get already some sense of what things look like. Obviously the top response is that we want to pass the course. And I think that goes for both the teachers and students alike. And then it's things about, basics of programming. And I think that's really what this first part of the course in period 1 focuses on. It's the essentials of the kind of concepts of programming and how to implement these concepts in Python. Quickly learning to analyze GIS data is probably something that becomes more of a focus in period 2 in the AutoGIS 2 course. But then some of these other, I mean, it's sort of alternating almost here that this is more like something for period 1 to learn Python and feel confident using it. And then analyzing GIS data is more of a period 2 thing. So those who are really interested in the geographic applications, you'll learn some fundamental tools in period 1, but they really like focus on applications to GIS will be more part of period number 2 in the AutoGIS 2 course. But yeah, we hope you have fun, and you're welcome to, of course, drink coffee carefully around your computer when you're doing that. And I think I don't know. I don't think ArcPy is really part of the.
Yeah. I'm sorry to say that we're not going to touch ArcPy. We are going to look into the same functionality within QGIS. So you're going to have some knowledge of how things interact with the desktop GIS, but with QGIS instead of ArcPy. So it's very similar in the end of the day. So you're still gonna get a taste of it, but maybe not ArcPy itself.
Yeah, but I think otherwise, again, this looks very nice and more or less in line with what we would learn in both periods 1 and period 2 of the course for those who continue on in AutoGIS 2. So I think maybe we're going to continue here. I don't think I ever showed the course webpage, so I just wanted to show that quickly before we continue. So this is what the course page looks like. And what you can see here is basically kind of overview of, well, basically the landing page for the course. So there's some general course information first over here on the left side, and then material that relates to our first lesson, lesson 1 for today. And then there's some resources down here at the bottom about things that might be useful to look at. If you look in the general info, you'll see things that we basically already have gone through about when the course takes place, who the lecturers and course assistants are, and then also some useful links for different parts of the course, still including the link here to the poll. So if we're asked to go use the poll again, you can always find the link in general info to get there. There are also some learning goals and grading, other things that you can go through here. So the learning goals maybe is something you might want to look through yourself. But I can say, for instance, in the first week, we're basically just introducing the course, explaining some basic ideas about what a computer is, what a programming language is, and then giving you just a very brief introduction to how to do a few things in Python. And then you can go through if you'd like and look at what the focus is for the other weeks of the course. So you'll find that in learning goals. Maybe it's worth noting about the grading, just because I'm not sure whether we'll come back to this at any other point, but it's a standard sort of distribution for how the grades are given in the course between 0 and 5. And 60% of your grade comes from the weekly exercises. So in contrast to some courses where maybe there's more of a focus on the final product or whatever that you do, here we have 60% from the weekly exercises and then 40% from a final course project that builds on the weekly exercises. So that's essentially how your grade will be determined. There are 7 weekly exercises and then a final course project. And yeah, I think that's that. Probably don't need to look at the license and terms of usage because that's not necessarily the most important thing for us to look at. But I'll also note here on the course page that we do have some resources. Our glossary is kind of somewhat functional. It's got a lot of placeholders where we said we'll give a definition for some of these terms in Finnish, which has not been done yet. But you can find definitions of certain terms that appear in some of the lessons here if you'd like to know what their definition would be in the glossary. You can also find some information about installing Python on your own computer if you'd like to do that. However, at the moment, we would recommend you don't do this yet until we resolve the issue with our computing environment, because we basically want to make sure that the instructions we give for installing Python here are compatible with what we would be, or with the cloud computing environment that we are normally using in the course. So installing Python on your own computer, it's a completely optional thing. And if you want to do that, you're more than welcome to do so. But and in fact, you can find kind of detailed instructions about how to install everything here. But I would hold off maybe 1 week before attempting to do that if you want to install on your own computer, just so that we can make sure that everything is synchronized and that the versions of libraries on our cloud computing system would be the same as you would install on your own computer. So everything works the same in both cloud world and on your local computer. And then maybe also just to note, you can find, if you want, some more resources to look at. There's a bunch of books we link to, Python tutorials and other kinds of things that teach you about various elements of the course, including a textbook that we're working on with some of the former teachers from the Geo-Python course, which I'll just open in a tab here. So this is essentially Geo-Python plus AutoGIS 2 in a textbook form. It's a work in progress, so it's maybe 40% complete, 50% complete, something like that. And then we have also some case studies. These are not yet described in any detail. But if you're interested, you can go and take a look at the materials we have for the textbook. It's a lot of the same material as in the Geo-Python course, but in a slightly more book-like format. So you can kind of go there and basically browse through any of the topics that you would like and see examples of how things work in how we've described them in the textbook. Might be kind of something to complement the Geo-Python course materials, although they're very, very similar in many cases. So yeah, that's the course webpage. I realize I've kind of gone through that a bit quickly, but I think this is probably best that you just know it's here and you can look through on your own. I mean, there's no need for me to read you the webpage contents. I think it's better that you just take your time when you have it to browse through things and find. We hope that the information is fairly easy to find here on the course page. And yeah, I don't know. Are there any questions? It's very awkward for me to try to have you ask questions, but if there are questions, maybe, I don't know, if someone wants to ask, you'd be welcome to do so.
It seems nobody has a question.
Okay. Very good then. So yeah, so the kind of plan here for the rest of the first part of the lesson today is we'll go through some little bit of motivation for the course and then a bit about the computers and programming languages. So I mean, the goals of this first half of the course, basically, as mentioned, are to introduce Python and how to program using the Python language, how to build these kind of basic programming skills, and then to talk a little bit about some good programming practices that we think are important for young researchers. So things that go maybe a bit beyond just like getting the computer to do what you want, but doing it in a way that is sort of easy for you to not only implement, but also to understand, to read your own code, to sort of do things in a way that you don't risk losing information or losing things when you modify your code, and that you can always go back and test earlier versions of what you've worked on. So there's some different things we'll introduce to help with these good practices for programming. But yeah, for the motivation, we're going to jump back to the course webpage here for just a moment. Maybe I'll move this out of the way and see if I can maybe make this a little bit bigger. Hopefully that's okay to see on the screen in the classroom there. So I think the kind of important thing to consider at the start of any course in programming, for example, is why would you want to bother with learning this skill? What is it, you know, how is it going to benefit you? And how are you going to sort of be in a better position as a scientist after learning a bit of programming? And you know, we basically want you to learn to program because we think it's an important thing to be able to manage data, to interpret and analyze data. But also, when learning this kind of basic skill, we want you to learn a few other things along the way as well. So we'll learn to program, but we're also going to learn how to write programs that are easy to understand. So that means that they're easy for both you and other people to read through, easy to share. We'll also introduce ways to keep tracks of the changes you make to your programs, which becomes kind of increasingly important as your programs begin to get a little bit more complicated, because sometimes you make a change that breaks things, and you want to be able to go back to a state when things worked. So we'll introduce a way for helping you to keep track of your changes so you can always go back. We'll also want to help with creating programs that make sure your science is reproducible so that your results can be, if you created a figure or something like that, that you can recreate the results on demand, which is a sort of important thing from the perspective of open science, that you not only have a plot, but you have the way to show how the plot was produced. And if someone wants to investigate, how you generated your results, you can say, okay, that's fine. Have a look. It's right here. And also at the end of the course, we'll talk about how to make some simple and effective data visualizations. So these will be ways to visualize the data that make it easy for someone to look at and quickly understand what you're working on. And so on that topic, we can talk just briefly about data visualization, because that's the direction we'll go toward the end of the course here, is we'll end up with data visualization. And, it turns out that this is actually quite an important thing to learn, because what data normally look like are things like this table here. So you'll learn in the course how to read in data files, how to analyze them in various ways, and how to plot the results. And the whole reason that we want to go through the exercise of creating the plots is that when you look at data tables like this, I don't know about you, but for me at least, it's very difficult to look through this data file and immediately go, oh, okay, I understand what the value of this data set is. It's there's a lot of different columns, there's a lot of numbers here, and it's visually doesn't really tell you a whole lot about what the data actually represent. So there could be a very interesting story here. In this case, we have a data set of these are global temperature data. I don't remember which location they're from, but it's data starting from 1952, and I think it's several times a day temperature measurements from 1952. I think maybe up until 2019 or something like that. This is just a tiny piece of it, but it's not that interesting to look at this. It's not very exciting. It's not very engaging to look at a data table like this. And of course, that's the reason that we want to visualize things to begin with, is to take a look at the power of what the data can convey. So one option to do that would be to use an XY plot of temperature versus time. So this is now going to be a temperature anomaly versus time. So this will be sort of a difference in temperature relative to some reference value. And in this case, we have data going from about 1880 until maybe 2015. And you can see here, by looking at the data this way, now we start to see a little bit of a picture of what this temperature data set might actually contain. And so a little bit of processing here, we end up with a very different looking picture of our data, where we can see in this period from maybe 1880 until around 1940, we had temperatures that were slightly below the average for the reference period. So the reference period in this case was the century from 1901 to 2000. Then we had a period of time when temperatures were kind of close to the reference temperature value. So between maybe 1940 and 1980, temperatures basically stayed very close to this sort of average over the whole 100-year period. But then from 1980 onward, we see this increase in temperature. And this is, in this case, global temperatures. And obviously, just looking at this right away, you see much more than you would from the data table we looked at just a moment ago. So this is one way in which we can look at things, and this is much more intuitive, much quicker for someone to understand. I think probably you could take this figure and show it to a family member who doesn't know anything about global warming even, and probably make a sort of case to say, look, here's evidence that the temperatures are changing globally in this plot. So this is a step in the right direction in terms of making things easier to understand. And there is, however, one thing that's kind of missing here. And that is that by taking this global data set and compressing it down to an XY plot, we've lost a little bit of information, and that is information related to the geographical locations of where these temperatures are varying. So another way in which we could look at the same data would be a plot that looks something like this, where we're seeing the difference in temperature. So this is, again, temperature departure from average for 1 month. So this is the month of January 2020, which you may recall was a rather warm winter month here in Finland. That's why we're in the sort of red zone here. So there was, in this case, a 30-year reference period from 1981 to 2010. And you can see, even compared to that reference period, we have temperatures that are considerably warmer in much of Northern Europe and Northern Asia. And in this case, we see a little bit different picture. We have a time snapshot, so we've lost the kind of change in time piece. So we're only seeing the temperature difference for 1 month, but we can now see in space how those temperatures are varying, and how in some places, while the temperatures may have been much warmer than normal, there are other places like Alaska where the temperatures were much colder than normal in the same month. So this is another way in which the same data could be basically analyzed in a different way to give us more information about what's in that data table in a visually appealing format, and again, something that's intuitive to look at. So yeah, a little bit different picture. And now I'll just show a couple other examples here, because it turns out it's a little bit tricky to combine both space and time in a single figure of showing something like a change in temperature. So oftentimes what people have done is to create nice animations. So here's a few examples of some animations that show temperature anomalies over time, and I'll just start this one off. So here we have different country names in alphabetical order, and then we have this sort of design of this figure such that you'll have different size and colors of circles that correspond to different temperature anomalies, and this will play through from year 1880 to 2017. Hopefully this works. And so what you get here now is a combination of space, so change in temperature spatially, change in temperature with time as well. And so you can then start to see not only places where temperatures year to year might vary differently, so some places where it might be warmer in one area and colder in another, but also these sort of trends. And hopefully with this one, you can clearly see that as you go closer and closer to the modern day, there's much more of the orange and red colors, almost maybe to a concerning degree. So this is a very nice example of a visualization showing this kind of temperature change data, where in the end here in 2017, there's not a single place where the temperature is not warmer than average globally. Another one, just to show as an example, is a sort of little bit different style of the same kind of plot. So this one actually goes further and even forecasts how temperatures should change based on global climate modeling. But what we have here now is a sort of a ring where a temperature anomaly of 0, so meaning it's the same as the average temperature, would basically be a bar that extends from the middle of the plot out to this ring here where I have the mouse cursor. Hopefully you can see that. And now the countries are sort of grouped a little bit more like geographically. So all the countries in Europe are here. So each of the bars then would correspond to one country in Europe, Asia, Oceania, Africa, South and North America all have sort of clusters of bars that relate to those geographic regions. And again, if I hit play on this one, you should see somewhat similar things now with the bar length representing how big of a temperature anomaly it is. Again, same kind of idea with the colors. So the more red it is, the more positive the temperature anomaly is, meaning the hotter it is compared to the average temperature. And so obviously, like we've seen, as you get to year 2018, for example, temperatures are getting quite a bit warmer. And now here is the forecast from this based on earlier climate models of how the temperatures would be expected to change and how temperatures anomalies should grow through to the year 2100. Obviously, this is concerning type of plot, but I think visually it's quite interesting to represent the data in this way, and shows quite nicely how much we can expect to see temperatures change. And again, combining space and time together, this is a rather nice visualization. So in the end, I think our last exercise, I'll tell you, we're probably not going to be creating things quite this complicated. I think we do end up making some kind of temperature animation where you can calculate a temperature anomaly, but it's definitely a little bit simpler than this. However, this is done in Python and can be found. I think you even look, I think for this, Antti Lipponen has some of these code available for producing some of these animations. So you can go and see how this is done. It just takes a bit of formatting to get the figure to look nicely like this, but we'll learn the sort of basics about how to produce a simpler version of this during the course. And that's kind of part of our motivation here, is to learn how to take things from a data table and put them into a visualization that makes it easy and interesting to have a look at the data we're dealing with. So this could be kind of our inspiration for the rest of this first part of the course. All right, I'm going to jump back here now to the slides, now that we're hopefully all very motivated. So yeah, as noted, in the first part of the lesson for today, we're going to learn a little bit about basic computing practices, some computers and programming language basics, and then take a look at the pieces that go into a computer program. So that's essentially what the rest of these lecture slides will be about. And once we finish with the lecture slides, we'll take a maybe 10-minute break, and then we'll continue with the rest of the lesson after that. And yeah, I think I've already kind of hinted at the question about, like, why is it worthwhile to learn to program? I think it's certainly a more or less essential skill for scientists today to know at least some programming. And the thing for us is that we recognize that, that you're not computer scientists. We're not computer scientists either, as the teachers. And I think that's an important thing, that we try to approach introducing the kind of ideas of programming to you from perhaps a perspective that's not the same as you might encounter in courses from the computer science department, for example, or their study programs. And so, yeah, we would say that, do you really need to know how to program? Absolutely. It's not about being someone who can write 10,000 lines of code to, solve some incredibly complicated problem, but just even simple, shorter codes that can batch process many different data files, do the same analysis to the same kind of data file over and over again, are very, very useful things to have. And it doesn't need to be, it can be 10 or 15 lines of code, but it can save you hours to days of work if you write a short code for dealing with the type of data that you're typically interacting with. And again, I think both geology and geography are becoming increasingly quantitative. So learning to program is more or less now one of your kind of core essential skill sets that you should have when you finish your degree from the university. So it's something that I would say, it's, to me at least, as important for the geology students, for example, as rock and mineral identification. I mean, it's a kind of fundamental thing that that's part of what you need to use going forward, and what you most likely will use going forward in your career, whether you go, into academia, private industry, or whatever. It's an essential thing. And I think that another thing from the perspective of many different pieces of software now is that there are a lot of softwares that have Python interfaces to them now. So you can basically take a piece of software that you're using, maybe to visualize some kind of data, and you can extend what it can do with a little bit of programming. So things like ArcGIS, ParaView, Google Earth, they all have Python interfaces to them where you can basically expand on what the core functionality of the software is with your own little codes. So that's kind of exciting. Here's an example from QGIS. So Christoph already mentioned that you'll be introduced to QGIS in the AutoGIS 2 course. And here's the Python console in QGIS. So you're able to directly interact with elements inside of your GIS software from Python. And again, depending on what kind of analysis you're doing, this can be a very useful way to extend what the software is capable of doing. I would also say that if you have an open mind to it, learning to program is actually kind of fun. So, I mean, kids now are being introduced to programming earlier and earlier in schools, and it is a skill set that if you are willing to kind of not let yourself feel overwhelmed, perhaps, with the concept, breaking things down, like complex problems, breaking them down into little pieces that you say, okay, I can kind of attack this one step at a time. If someone said, okay, I want you to make me a nice animation of this temperature anomaly data through time, and I'd like that tomorrow, or what I mean, like, okay, that's kind of a crazy request, but trying to sort of take that complex problem and say, okay, how would I approach this? What are the small pieces that are needed to begin to pick this apart? It's kind of a fun thing to do, and it's like solving problems, setting up strategies, testing your solution. All of these things, once you learn a little bit about how to do it with the programming language, can be a lot of fun to use. And of course, this can also be very rewarding when the code works, which unfortunately is not all the time. So let's talk just a moment about ways in which programming could make us better scientists. So hopefully you have some idea of what the scientific method is before. This is kind of the fundamental paradigm by which most scientists would carry out the research that they do. So, this is just the kind of overview of the steps, but there's some kind of question that you would define. There's information that you would gather. So you might collect your observations or papers or whatever, gather your resources, might come up with then on the basis of those resources, some kind of hypothesis you want to test. And then you would test your hypothesis using an experiment. And of course, using an experiment could be very broad in terms of what that means, but you basically want to do something to try to test your hypothesis, collect some data as part of that process, and then analyze the data, make some interpretations, and then hopefully publish your results, and then possibly retest, which is maybe not something you would do, but it's something that could be done by other scientists. So that's the scientific method in general. And if we look at that from the perspective of how programming can help, there's a number of places where programming alone can chip in. I would say that some of these things that are in gray here are probably could possibly be shading toward blue with various developments in AI and things like that. But at least for right now, let's keep this in the perspective where the humans come up with the questions and the humans form the hypotheses rather than outsourcing that to the computer. But gathering information and resources, obviously you can, I think Christoph is someone who's very familiar with things like scraping things from the web or from various kind of data sets that are kind of dynamic and changing all the time. So, gathering in information from various places online or elsewhere, other kinds of data sets, the computer can be very helpful in doing that. Performing an experiment and collecting the data. I think the sort of experiment part, essentially if you've written a code to test some hypothesis, you can very easily see how that's useful. Data analysis is something we'll do in the sort of second half of the first part of the course. So the sort of weeks 5 and 6 of this course we'll get into doing data analysis using a library called pandas. And that kind of data analysis is something where it could save huge amounts of time to use a program for that. And of course, interpreting the data, visualizing things, and the computer can do this stuff much faster than we can do it by hand. And so clearly, programming can be helpful there. Now, good programming practices. So in addition to what the program itself can do to benefit us, good programming practices can help us with things like making sure that what we do is reproducible. So again, with the ideas that are kind of fundamental to open science, reproducibility is one of the key things, and having a way in which you can say, here's my data and here's my script to analyze the data. That's something that can be very useful. With a little bit of effort, we can then very easily have possibility to reproduce results, no problem. And the same goes for retesting results. You can share your code with someone else. They can retest things very easily. So obviously, learning to program can be quite useful. Now, I think I'll take a slight break from speaking for just a second here. And we'll ask a question, that is, what is a computer? And if you think about that for just a second, you can go here to the polling page once again. I will put the question up, so give me just a second to do that. And I don't want to give away the answer here. Let's make our question visible. You should be able to hopefully see the question now, so you can go to the polling page and fill in your ideas for what you would consider to be a computer. And again, like the previous question, you can also click on someone's response if you think that's an idea that you support. So let's take a minute, fill in some responses about what's a computer, and then we'll continue from there. Okay, so let's see. Looks like things are starting to slow down. Of course, you can still add your responses as you like. Box Full of Magic is the current leader, which, while that may feel that way, it's probably not a very accurate technical definition of what a computer is. So, yeah, I suppose to some extent it may well be a box full of magic. But I think the second option here, a machine you can program to do things, is probably closer to what most kind of engineers or computer scientists would consider a computer to be. It would, of course, include some kind of hardware, but the hardware by itself is not necessarily sort of a complete definition of what the computer would be. And the strings of ones and zeros would probably be more like what a program could be interpreted by the computer to be, rather than what the computer is itself. And a machine you can program to perform various processing tasks. I mean, I think these are quite similar. And of course, the devil's work, I suppose that depends on your perspective. Glorified calculator. Yeah, to some extent, it's not a terrible definition, to be honest. It is in some ways a glorified calculator. And of course, there are some other options here as well. But I think that basically, the sort of idea of a machine you can program to do different things is the essence of what we'd be looking at for a computer. Then if we just continue from here, your definition was actually pretty close to the definition that I would take out of a computer science textbook, and that is a computer that is a machine that stores and manipulates information under the control of a changeable program. So if you strip this down to its sort of most basic elements, this is what a computer would look like, where you have some kind of input device. For us, like for me right now, I guess it'd be like my trackpad, the microphone, maybe the video camera, and my keyboard. Those would be my input devices. Inside the box, this could be our box of magic if you like, we would have some kind of processing unit, CPU, and that does most of the calculation of handling the information that comes in. Sorry, in from the input devices. It may need to store values from the calculations in the main memory and retrieve them from the main memory. So those two things are inside the computer. And then that information will be, for instance, sent to a display or to speakers or whatever, or possibly written out to like a hard disk for the example. So the key parts of our definition here is that this is a machine that stores and manipulates information. So information can be input, modified, and then output in some hopefully useful way for our interpretation. So that's one piece of it, is that we're manipulating, we're processing information. The other thing is that it's controlled by a changeable program. So most kind of firm definitions of what a computer would be would rule out something like a basic calculator. So the kind of standard calculator you might find in like a desk drawer in your parents' house or something like that. That calculator, if it's not a kind of programmable or graphing calculator, isn't really a computer. It has a fixed set of operations it can do. The program can't be changed. It's kind of a hardwired thing to add, subtract, divide, multiply, and maybe do a couple other things. But a computer is driven by a program that can be modified. So, when you install a new update to your operating system, maybe it adds new programs or changes the functionality of the programs that you have, might patch security holes or whatever. But the changeable program is kind of a key part of the computer as well. So it's under the control of this program that can be changed rather than something that's hardwired in there. You could also ask the question of what computers are good at. Well, in general, they're good at well-defined and clear tasks. Computers don't really like when you give them something abstract to do. So if you tell the computer to add 2 + 2 and return the answer, and you speak to it in a language it understands, so this is an example of printing out the value of 2 + 2 in Python, and you see very obviously, as you would expect, that the value is 4, and the computer would have very little difficulty with that kind of calculation. Computers are also good at storing data, manipulating data, doing repetitive calculations. This is probably one of the things computers are best at, is just doing the same kind of calculation over and over again, as well as processing data or instructions. So, if you give it a very well described task, then generally the computer will not have too much trouble with that. We'll skip that thing for now. So what are they not good at? Well, poorly defined tasks or abstract tasks. If you gave the computer the instructions to calculate pi, it's not like the computer can't do that mathematically, but if you don't tell it what kind of equation to use or how what the program is to calculate this value, then it's going to have a difficult time doing that because it simply needs to have clear instructions in order to do such a calculation. Of course, it's not hard for the computer to do. This is the first 1,000 digits of pi, and it wouldn't be a big deal for a computer to calculate this if you tell it how to do that. Computers are also not good at tasks that are simply not computable. So if you ask a computer where your car keys are, probably it's not going to be able to compute that because it doesn't have information related to where your car keys are unless you have some kind of, I don't know, one of these little tags or something on there that somehow tracks the location of things like your car keys. Probably it's going to have a hard time with that. And even if you were to do that, to try to run that calculation on the sort of most massive supercomputer in Europe at the moment, the Lumi supercomputer with about 200,000 processor cores, it still is not going to be able to find that without some information about how exactly it's meant to locate your car keys. And there are other kinds of problems that simply can't be solved or require too much computing power, even for a supercomputer like this. So if you asked a computer to calculate the forecast of how the temperature would change at 1 millimeter accuracy across the surface of the planet for the next 10,000 years, it's probably not going to be able to calculate that simply because the size of the calculation is too big for the computer's memory to process. Okay, so let's talk a little bit about what a program is And here's a couple examples of some programs here. An old school Fortran punch card from back in the days of programming on punch cards. So these would actually be the equivalent of how you would write your code today, but you'd have a whole stack of these punch cards that would then be fed into the computer to do basically to execute your code. And then here's a more recent example of some kind of Python source code that shows things that are maybe a little bit easier to deal with than Fortran punch cards these days. But in essence, the program is just a detailed list of step-by-step instructions that tells the computer exactly what to do. So again, we don't like ambiguity. The computer doesn't like to have uncertainty about what to do. So for instance, here, we've got some variable, and the variable 1 is going to be equal to whatever this other variable's value is at some location here. Or for example, the variable PTS, or PT size, equals 40 is another example of very clear information that the computer should store the value 40 in a variable called PT size. The program can be, of course, modified to change what it will do when we execute it, and software is just another name for a program. So if you're familiar with that word, it's basically just a synonym for program. Now, for programming language, it's essentially the language that the computer will understand when we try to talk to it. So, you know, the computer language itself is maybe what we would use to talk to the computer. But for us, the language the computer really understands deep down is still kind of ones and zeros. And so for us to talk to the computer directly in its language that its processor would understand is maybe not ideal. But we can use things like programming languages that are a list of instructions that we can perhaps understand, and that we can also then feed to the computer, and it will understand, because the programming languages are designed to be exact. They're designed to be unambiguous, which means there's no lack of it's very clear to the computer what everything in that programming language means. So it doesn't have to kind of question what you meant when you use the word print or something like that. And every structure in the language has a precise form, which we can call the syntax, and a precise meaning, which would be called the semantics. So, you know, you've maybe seen syntax errors before when you've used other programming languages, and that basically just means that you've given some kind of instruction to the computer in the programming language in a way that the computer didn't understand it, meaning you've had a mistake in how you've typed something in, and then the syntax is incorrect, which means the computer doesn't know what to do. And Python, of course, is just one of many programming languages, as we already saw in the poll earlier. And sorry, couldn't find my mute button fast enough. Okay, so I think we've got maybe just a couple other slides here, and then we are due for a break. So hang with me for just another couple minutes, and then we'll take the promised 10-minute break. So when it comes to programming, maybe I should note a couple things. One is that these slides are, you know, we're kind of going through them maybe a little bit quickly. They'll be on the course page. You can go back and have a look at them. They're really kind of underlying some of the elements of things in the course that you probably are already familiar with. So I'm kind of assuming some familiarity with some of the ideas of like what a computer is and what a programming language is. We're giving a little bit of detail here, but it's not that you're going to be necessarily referring back to these slides when working on the assignments, but just so that you have them as a reference. But yeah, when it comes to creating a program, there's basically several different steps that we're going to follow in most cases. And it's actually kind of a good idea to approach these kind of programming problems, not from the standpoint of like, let's jump in and start coding right away and find a sort of solution, but rather take a few steps beforehand to think about the problem you're dealing with, create a kind of good idea of what you're going to do, and then code it up only once you have a clear picture of what you actually want to do. This will save you time, even though it might seem like it's more time consuming because there's a couple extra steps to follow. But the basic strategy for most programming problems you try to solve is that you first want to figure out what is the problem. So to analyze the problem you're trying to solve, determine what information you need to be able to solve that problem. And then you can create some kind of design of a program that would be able to solve the problem you have, implement the design, and then to test it, and then, if necessary, maintain the program you've created. So if you anticipate other people might use it, then of course you may need to update things as needed. So I always like to use my silly example of as an American growing up in a country that used Fahrenheit for temperatures. So 70 degrees Fahrenheit is quite nice. 90 degrees is quite hot, and water freezes at 32 degrees. And as I typically note, it's very intuitive, as you can see. The problem here, of course, is that now living in Europe, I can't use my sort of familiarity with Fahrenheit to tell me what clothing to put on when I get a sort of weather forecast with temperature in Celsius. So my proposal is that a simple program could help in dealing with this problem. So step one is going to be to analyze the problem. So before we can solve it, we have to figure out what we need to do. So in this case, I think it's pretty clear. What I want to do is I want to figure out some way to take a temperature in Celsius that I might get from some weather webpage here and convert it to Fahrenheit, so I actually know what clothing to put on to be able to go outside and be comfortable with those temperatures. Once I have figured out what the problem entails, I can then determine the specifications. So basically, this is what is the program going to do, and I want to try to be somewhat precise about this. So I don't need to worry about exactly how it's going to work, but I do need to say what it should do. And in this case, it should do something like maybe take a temperature in Celsius and convert it to a temperature in Fahrenheit. That would be a useful thing for the program to do to help me out. So, but again, we're not worried about how this is going to function in the code or anything like that. It's just like what's the kind of steps to dealing with the problem. Then I can create a design, so the kind of overall picture of how the program would work. And this is actually something that you can do in the form of what's called pseudocode. So you can write this out in Finnish or in English, whatever you prefer, or whatever your native language might be, if you want to use that. That basically describes the steps of how the program is meant to operate. And in this case, again, you want to be specific here because basically this is kind of making your template for how your program is going to work. So here, what you can do is you can write out basically, okay, first, I should have, the user would input a temperature in Celsius. Next, the temperature in Celsius would be using some equation converted from Celsius to Fahrenheit. And then the third step could be that the temperature in Fahrenheit would be printed out to the screen. That would be an example of the sort of pseudocode where you sort of say step by step what's going to happen in the code. You might even include things like what is the kind of equation we would use to convert the temperature from Celsius to Fahrenheit, so that it's very clear how the code is meant to work. So once you've hit that step, you basically have a very clear picture of what your code's meant to do. And now you can essentially translate your pseudocode into something like Python or whatever programming language you want to use. So this step number 4, the coding part, actually can be a fairly simple thing to do because you already have a pretty good picture. If you understand a little bit about the kind of things you need to use in Python to do this, this fourth step could actually be something you could do fairly quickly, assuming that your pseudocode has given you a good picture of what you need to solve in order to be able to implement your code design. After that, of course, you want to maybe do some testing and debugging of your program. So typically, for something like a temperature conversion program, maybe you would want to take values and convert those from Celsius to Fahrenheit. So I would expect, for instance, if I put in 0 degrees Celsius, that 32 degrees Fahrenheit would be the value that my program would output, because it should convert from Celsius to Fahrenheit, and it should give me the temperature of water freezing in Fahrenheit. I could also put in some other values there, for example, but just to make sure the program is working, I would probably want to test a few known values and make sure I get these known values back. Before I start doing conversions and values, I don't necessarily know what the value should be automatically after that. So, but yeah, I mean, otherwise, how do you know if your code works? You know, you don't, like, it might give you something that looks like, yeah, okay, that seems like a reasonable value. But if I put in, 20 degrees Celsius and it tells me it's going to be 140 Fahrenheit, and so I go outside, in the sort of like my shortest shorts and tank top or whatever, because it's going to be so hot out, and then I'm like, oh, it's actually like it's not that hot at all, or whatever. It could be much worse. I guess it could be, telling me it's going to be warm according to my Fahrenheit temperature when it's actually freezing outside. Then obviously my program is going to be not so useful. And finally, there may be a need to maintain the program if you're expecting other users to be able to use it. Sometimes this means that you might have to sort of update the program if the library you're using changes or things like that. But we'll come to that maybe later in the course. But overall, that's the kind of picture for how to create a program. And since we are coming up on break time for sure, I'm ready for it, and I'm sure you are as well. I'll just recap quickly with the kind of idea of what a computer is. Well, our definition is basically it's a machine that processes information or interprets and interacts with information under the control of a changeable program. And so I think those are two kind of key pieces there. In terms of what a program is, well, essentially it's just our list of detailed step-by-step instructions for the computer that tells it exactly what we want the computer to do. And again, computers don't like uncertainty very much, so it's expected to be exact in the instructions that we're giving to the computer. And then some of the steps in developing a program, well, we've just gone through them, so I think I'll skip that for the time being. So at this point, yes, why don't we take 10-minute break or 11-minute break, come back at 10:40. And yeah, you can, stretch your legs a little bit. We'll continue at 10:40 and we'll continue from the course webpage here. So I'll just leave this up like this and see you at 10:40.